So this is a model, right? That has kind of some, conceptual merit. It's not exactly how the Earth works, but I wanted to talk about a model of incoming solar radiation. First of all, solar radiation comes in what we call shortwave radiation. So we've got the sun up here, looks like a balloon or something, kind of shooting energy down into Earth. Now, the energy that we get from the sun is shortwave radiation in the context of the electromagnetic spectrum. Hopefully you guys remember that everything emits radiation in one wavelength or another, depending on its heat. Well, the sun's pretty darn hot, right? So it emits shortwave radiation that's vibrating really, really quickly. Too quickly to actually interact with the atmosphere. So that visible light punches through the atmosphere, no problem. And then that energy is absorbed into the Earth. So that energy is stored there, and then that energy radiates back from the Earth, but this time in the form of long-wave radiation. This is an interesting concept I read just recently. I'm thinking about energy in, changing a wavelength, and then energy out. So first, an interesting concept that I read about was a factory of some sort, right? So in one side of the factory, they have a receiving bay, and they get small bits of metal and nuts and bolts. And out the other side of the factory, they're sending washing machines or whatever, right? You could kind of model those in your mind as shortwave radiation, so this energy, and then long-wave radiation coming out. But it's kind of the same stuff, right? It's just organized differently, and it's larger coming out, but it's made out of the stuff that came in. Shortwave radiation and emitting long-wave radiation is kind of like that. Now, if we go back to our factory example and we think about, well, if they are getting more nuts and bolts shipped to them than they're using, then is kind of going out of the system, eventually the factory will fill up with nuts and bolts. And if we were to receive more shortwave radiation than were remitted by longwave radiation, the Earth would cook, right? It would become as hot as the sun. It would reach that kind of solar constant, right? 1,300 watts per meter squared. The opposite is true, right? If they're making washing machines faster than they're receiving nuts and bolts, the factory's going to shut down. And in this case, if you were losing long-wave radiation and not getting incoming shortwave radiation, things would get colder and colder and colder because that heat wouldn't be trapped. So what we kind of think about is the atmosphere in this, what we call one-layer model, is really that throttle, right? So as long-wave radiation is absorbed into the atmosphere, it spends a little bit of time here. That's kind of the next step, right? So the energy is brought in the form of shortwave radiation from the sun, absorbed into the surface of the Earth, and then from the Earth remitted in long-wave radiation, which can't get through the atmosphere. And when that long-wave radiation hits these molecules, those molecules begin to wiggle and send radiation off in a spherical pattern, very similar to the way that the sun did. So some of that radiation goes off into space, and some of that radiation actually goes back down to Earth to get re-emitted and to kind of bounce around a little bit. I think you watched a video about the ping pong, or not the ping pong ball, the pinball example. So this is the greenhouse, right? This is actually how a greenhouse works, although in that case we have a solid piece of glass or polycarbonate rather than, atmospheric gas concentration. So I want to put some numbers on this and just kind of give you an idea of where the energy fluxes is happening. And this is also going to help us when we get into the next video talking about clouds and how water vapor is associated with this. So this is the primary thermal regulatory system of Earth. And remember, we've got, so going back to quantifying energy, we've got 238 watts coming in to the Earth on average, every square meter, right? We know the caveats that exist here. And then that 238 initially, I'm not going to write this number yet, actually goes into the atmosphere. It has to. The same amount of energy has to go into the atmosphere. Otherwise, it would be a molten lava planet. Once that energy is in the atmosphere, that same amount of energy is emitted in 3 dimensions, right, in this sphere. So we've got 238 going out to space, and we actually have 238 coming back down to Earth, remitting into the surface of the Earth and beginning again its cycle as long-wave radiation. So that actually means that from the Earth heating the atmosphere, we have twice this amount of energy. We have feeding into that atmosphere, we have to have 476 watts, using these numbers, of energy to actually counterbalance the amount brought back down from the atmosphere that's offset by the amount coming in from the sun. This atmosphere here is basically like the brakes, right? Imagine if this energy were kind of going up and it's getting stuck in some jello on its way to space, and that jello is sticking energy out in every direction. If there's lower concentration of greenhouse gases, so lower methane and CO2, that energy can leave more quickly. The moon has no atmosphere, or no appreciable atmosphere, so it has these huge, almost 200-degree temperature cycles every day. Here, we have just the right level of insulation to keep Earth habitable for us, right? And again, in a place like Venus, where this is significant, shortwave radiation comes in and is basically trapped. There's molten lead on the surface of Venus, right? Kind of famously. It's hundreds and hundreds and hundreds of degrees Celsius. So changes in CO2 fundamentally change the temperature that we see down here. And what we're going to explore in the next video is how this energy can actually drive evaporation and leads to differing amounts of water vapor in the atmosphere itself. Okay, I'll catch you then.